So in the last class, you can recall, we wanted to know how do line elements transform. Okay, so that's what we are going to learn today. So we again draw the reference configuration and the deformed configuration. And think of a point here denoted by capital letter and the corresponding point in the deformed configuration denoted by small letter. Okay. And then we think of a material line element in the reference configuration. And starting from capital X. Okay. So starting from capital X, there can be so many lines, but we concentrate on one of the line elements. Okay. Whose other end is at capital X plus delta capital X. All right. Now you see, as this body deforms, in the general case, this line element will become curved, isn't it? Because you see this line element is engraved in the body, and as the body deforms, the particles on this line element need not be on a straight line even after deformation. It can get curved. All right, so let's denote the final point here by small x plus delta small x. But you see, as you take the line elements to be very, very small, this curve over here, curve starts to look like a straight line. If the magnitude of delta x, this goes to 0. Because you see, any curve, you can always approximate it as a straight line. But that approximation will be good only if the curve is very, very small, if it is very, very tiny. Okay? And we are looking at very, very tiny material line elements. So therefore, we can replace that curve with a straight line. Okay? So our focus is on tiny material line elements. And why is it so? Why are you looking at tiny line elements? Because I want to understand deformation in the small neighborhood of a particle. So think of this particle here, big X, and a small neighborhood around this particle. So it's a sphere around that particle. And this neighborhood is supposed to be really, really small. Therefore, any line element within that neighborhood would also be very, very small. Okay? So this is that neighborhood, which is also tiny. So basically, we want to concentrate on deformation very close to this point capital X, very close to it. So you have to start zooming at point capital X so that you start seeing things very clearly.
And then
All
here
right.
there will be a circle with radius delta x, capital X.
Well, this is a sphere. See, it's a three-dimensional body. So neighborhood is a sphere.
Sphere. Okay.
Yes. And this line element need not be on the surface of the neighborhood. It could be also within. So the radius of a sphere is not magnitude of delta x, because delta x could be even smaller than that. It just has to lie within the neighborhood, inside the sphere.
Okay, sir.
Okay. So can we see when we said I want to relate this line element delta capital X to delta small x. So how can I relate this? So delta capital X to delta small x. How do I relate? We know the deformation is given by this deformation map, small f, right? This is what we learned in the last class, and which changes with time as the body deforms, as the body undergoes motion, the deformation also changes. But our goal finally is to relate undeformed and deformed material line elements. Okay, so to do that, we can do the following. So we know that small x is equal to this f of capital X comma t, isn't it? So likewise, small x plus delta small x. Can we say that this is equal to f of capital X plus delta capital X comma t? It's just two different points getting mapped. Capital X getting mapped to small x, and capital X plus delta capital X getting mapped to small x plus delta small x. All right, very simple. And you have to recall that this f is a vector function. It has got three components because the point is lying in the three-dimensional space. So if I subtract these two, what do I get? So I get delta small x is equal to f of capital X plus delta capital X minus f of capital X comma t. And you see everything is being looked at the same time. So in the first argument also, it's at the same time t. It can't be that you for capital X you look at small t, and for capital X plus delta capital X you look at some other time. Okay, because I want to understand deformation at a given time, so it has to be at the same time. I'm not looking at velocity or acceleration that I take the time derivative. I'm looking at deformation at the same time. Okay, now what could be the next step here? Now, as we know that delta capital X is really close to 0, why don't I do the Taylor's expansion? So let us do its Taylor series expansion. But you see now it's a vector function of multiple variables. It's a function of more than one variable. So big X has got three coordinates, big X1, big X2, big X3, and also the time t. Okay, so how do I do its Taylor's expansion? So it's basically we have to perturb each of the components. So we could write this as del f. Well, first of all, the function itself at capital X, because I am doing Taylor's expansion at capital X itself. So this is going to become f of capital X comma t plus del f over del capital X1 into delta capital X1, isn't it? Plus del f over del capital X2 into delta capital X2. And likewise for the third one, so I could simply write this as del f over del capital Xi into delta capital Xi, isn't it? And there is no differentiation with respect to time because time is the same t. It is not t plus delta t. And then I subtract, well, then I have higher order terms also, right? Higher order terms. So I'll just write it as plus h o t, higher order term. And then we subtract f of x comma t. Okay, and you can see that the first and last cancel. So these two cancel. Now let us try to explore this higher order term. What is this really equal to? So what will be the next term in the Taylor series? We have to take the second derivative, isn't it? So it's going to be half of del 2f over del x1 2 into delta x1 whole square plus del 2f over del x1 del x2 into delta capital X1 into delta capital X2 plus del 2f over del capital X2 whole square into delta capital X2 square, isn't it? Then you have even higher order terms. Now let us see what is this in the matrix form. So if I think of the matrix form, um,
Uh,
yes,
sir, no, capital X3,
sorry, I can't hear you. Please repeat.
sir, capital X3 terms. So
Yeah, yeah, okay. So that is also there. Yes. So it has other terms also. But can you see that we of course have the derivatives, but the deltas are quadratic. Can you see they are quadratic, isn't it? What do you think? Does it seem like it is quadratic? Anybody? All the terms are quadratic here. And then when you look at the cubic term in Taylor series, all the terms will be cubic in the components of delta x. Okay,
yes,
so now let us try to write this compactly. Can I write this compactly? Now the same expansion f of capital X plus delta capital X comma t, because now you guys know about derivative with respect to vector, the gradient. So I can now introduce the following terms. I would say this is equal to f of capital X comma t plus, look at this thing over here. It's the first derivative. So can I write this as gradient of f, okay, into delta capital X? Will you allow me to write it like this? And we already know what is the gradient of a vector. So if you, for example, let me expand this, okay? So what is this going to become? del fi over del xj ei tensor product ej, isn't it? Because gradient of a vector, it's a second order tensor, and then I have to multiply this with delta xk ek, which then becomes del fi over del xj ei delta xj. Is that correct? Because you see ej dot ek will be delta jk, and delta jk into delta xk, that becomes delta xj, which is same as del f over del xj delta xj, right? And you see this is what it is here. It's the same thing. But now I have written in a tensor form. And what do you think the higher order term will look like? The higher order term, so if I continue, it will be second gradient. It will be gradient of f. Okay? And there will be two delta x's multiplied with it. So delta x, okay, maybe I should use another color. So I'll write it here, plus gradient of f. So it's a third order tensor, isn't it? One gradient makes it second order, another gradient makes it third order. Then this third order is multiplied with delta x to make it a second order. And finally, this is further multiplied with delta x to make it a first order. Because you see all the terms here are first order. So this is the compact notation for what we have here. Okay? But what I want to say is that this is proportional to square of the magnitude of delta capital X. This is proportional to square of magnitude of delta capital X. Because you see there are two delta capital X's here. If there are only one delta capital X, it becomes proportional to magnitude of delta capital X. But because there are two of them, it becomes proportional to magnitude of delta capital X square. And likewise, you have more terms in the Taylor series. So this whole thing, so I'll write this whole thing as f of capital X comma t plus grad f into delta capital X plus a new symbol here. And this is called big O. So that's a symbol for in mathematics. It's a function big O. And what is the meaning? So, whenever we say, let us say f of x is of the order of x, if it is like this, then it simply means limit x tending to 0, f of x by x will be some constant. And critically this means fx and x go to 0 at same rate. See, if fx were going to 0 quicker than x, suppose fx was x square, so fx is going to 0 quadratically. And so if you divide x square by x, it is x and then it becomes a 0. So fx is then not of the order of x, then it is of the order of x square. Okay, so therefore here, this term here that you see, that's of the order of delta x square. As delta x magnitude goes to 0, this green term, that is going to 0 at the order of delta capital X square. And then, in this Taylor series, there are other terms also, cubic, fourth order. So it's all in here. So the leading order is delta capital X square, and then delta x cube, 3, 4, 5. So all of them can be combined and written as the delta capital X square. So the highest order term, whatever is present here, that we will write here, the leading order term. Are you guys with me on this? See, it's a new concept, but the nice thing is I have just written everything compactly, and I also know exactly what is this higher order term, what is this extra term. Are you following me? So for example, suppose fx is sine of x, then can you tell me what is the order of x? Sorry, what is the order of fx? So I have to simply evaluate this thing on the left hand side. So let us try to evaluate this. So limit, we have sine x by x, x going to 0. And what is this equal to? This is 1, right? All of you know this. So this implies fx is of the order of delta x. Because when we divide by x, it is becoming a finite number. If it were sine of x square, let us say if fx was equal to sine of x square, then when I take the limit sine x square by x, it is still equal to 0. So that doesn't mean that fx is of the order of x. I have to divide by a quantity and see when it is becoming a finite number, some non-zero number. So then I do another exercise and say limit x tending to 0 sine of x square by x square. And when I do this, I will see that yes, this is equal to 1, a finite number. So this implies sine of x square is of the order of x square. Are you guys with me? Just a simple mathematics, but it is very useful. So this is called big O. And likewise, there is also something called small o. But I'll not introduce that now. I'll see if I need it. But you can look for it on Wikipedia. Look for the meaning of small o x. So that's small o. Okay? Are you guys following me? Roshan?
Sir, so whatever is the index in the denominator when we are calculating the limit of fx by that x, so whatever is the
Yes,
index of the denominator will be the order of the function.
that is true. Yes. You could also, you did not express order as powers of x. You can compare a function with some other known function also. For example, a function could be very, very complicated. But if you know of a very simple function, let us say g of x. So fx is very, very complicated. So let me write that also here while I'm saying. So suppose fx is quite complicated, very big expression. And so that it is difficult to know what is the behavior of this function as x goes to 0. It is difficult to know. But suppose someone says and there is a simpler function g of x, okay, and it turns out fx and gx are of the same order as x goes to 0. So this implies, so if fx and gx are of same order as x tends to 0, so that means limit x tending to 0 fx by gx is equal to a finite number. Okay, so this limit will not be equal to 0, or this limit will not be equal to infinite, because they are of the same order. And then we can say that fx is of the same order as gx. So we can also write like this. And the advantage is that we are comparing this complicated function with a very simple function g of x. And this could be useful, let us say, while finding out the limit of the function. This could be useful. You could simply replace f with g. Okay, so basically this big O thing is for comparison purpose. Can we compare a given function with some very simpler function? So that's where big O is used for. Have you learned this in continuum mechanics?
No, sir, we haven't learned.
Okay. Okay, so
Hello,
that was
sir, I had a doubt. Uh,
yeah.
Sir, in the main expression of f of capital X plus delta capital X comma t, we are writing this order of delta x mod square. So there are cubic terms and all in that expansion, right? So
Yes.
how did we take this leading order as square term only?
Okay, that's a very good question. See, so in mathematics, so suppose you have a function, so it's good that you brought it up so that I can clarify it even more. So suppose your fx is x squared plus x cubed plus x to the power 4. Okay? Then you again do that limit analysis. So limit fx, sorry, limit x tending to 0 fx by x squared. What does it come out to be? This will be 1, isn't it? Even though these are present, it is still 1. So this simply means fx is of the order of x squared. So when I say a function is of the order of x squared, that means it has got this x squared term, and it can also have the other terms, other higher order terms. It can also have that. And for all of them, you can simply replace them with this big O x square. Okay? Is that what you're asking, Niranjana?
Yes, sir. Yes, sir. Now I understand.
Okay, so basically, in this Taylor series expansion for f here, I have these two terms, and then the next one is this thing over here. Okay, so everything else is inside this big O, delta x square. Okay, so now let us try to see, I mean, our original question, how are line elements transforming? All right, so with this in hand, I can now say that delta small x is equal to gradient of f into delta capital X plus big O delta capital X whole square. Isn't it? And this gradient here name, and it's also expressed as big F. It's called deformation gradient tensor. So a small f is the deformation map and big F is deformation gradient. Okay, and if you write this big F in Cartesian or in E1, E2, E3 coordinate system, you get a matrix. Okay, so its representation is a matrix whose components are del fi over del xj. All right, and you see now, as I decrease the length of delta capital X, as I decrease the length of material line element, this big O term is going to get smaller and smaller compared to the first term, right? For example, suppose that the length of delta capital X is 0.01. What will be this one, this big O? It is 0.01 square. So it's very small, right? If you make it 0.001, 10 to the power minus 3, then this big O becomes 10 to the power minus 6. And we are going to take line elements to be infinitesimally small, really, really small. So in that case, can't we simply say that delta small x is equal to this big F times delta capital X? Isn't it? For infinitesimal line elements. Okay? So basically, let me come back to the picture. So if I want to know how do line elements transform about a point capital X, all that I have to do is find out the gradient of the deformation map and multiply this gradient with the line element. So as you multiply, you get the line element in the deformed configuration. And you see, it's a second order tensor. You can also think of it as a linear transformation. And what does linear transformation do? It takes a vector from one vector space and transforms it to another vector space. And in the spatial case, the two vector spaces could be the same, which we did in the class. But the two vector spaces can also be different. So here also, this deformation gradient tensor, it's a linear transformation, which takes the vector or the line element from the reference configuration and gives you the line element in the deformed configuration. Very simple. Okay. So this is how the line elements transform. Are you guys with me? I hope it's not getting abstract. You can also think of a specific example. So suppose your function f, so little x is equal to f of x, and let us say I write this in the E1, E2, E3 coordinate system. So this is equal to, think of any example. What should I say? Let us say this is equal to big X1 plus a into big X2. Okay, and small x2 is same as big X2. Small x3 is same as big X3. Okay, so think of a very simple deformation map like this. And we'll show it that it actually turns out to be the case of shearing. Some of you may have seen this also, that this is the example of shearing. But I'll also demonstrate it later on. So if this is the deformation map, what you have to do is first find out the gradient, big F. And in this case, you find out the matrix, because I have to work with some coordinate system. So what will be the matrix? The first term will be del small x1 by del capital X1, which is 1. All the diagonals will become 1. Then del small x1 by del capital X2 will become A. This is 0, 0, 0, 0, 0. So that will be the deformation gradient matrix. And once you know this matrix, and you see that this matrix turns out to be constant. It's not a function of x1, x2, x3. It's a constant matrix. So this is an example of a deformation where the deformation gradient is constant. But that need not be the case always. For example, if I include an extra term here, plus b times x3 square, then I get here 2bx3. So in this case, the deformation gradient becomes a function of the point where you are evaluating it. So as you change your point big X, the deformation gradient will also start to change. So the linear transformation will change. And accordingly, the material around the point will transform differently. Isn't it? So you see, come back to this example. So a neighborhood around capital X transforms to a neighborhood in the deformed configuration. Maybe say it's here. And this transformation is through the deformation gradient at capital X, because all the line elements are transforming through that deformation gradient, right? And as you change the neighborhood, as you change from capital X to another point, let's say capital Y, you will have different deformation gradient at capital Y. So the neighborhood will transform differently because the deformation gradient changes in general. Okay, I hope you are getting what I'm saying. So for a general deformation, deformation gradient changes from point to point. For a general deformation. Capital F changes from point to point. Okay. Can you give me a time? I think I'll just come in 2 minutes. All right.
Fine, sir.
Okay. Sorry. So I'm back. I hope you guys are there. Okay. So for a general deformation, F changes from point to point. But in case F is constant over the body, then it is called homogeneous deformation. So that's a special case, homogeneous deformation. Okay. All right. So this was about the importance of deformation gradient tensor, which maps line element from reference to deformed configuration, and accordingly it maps a neighborhood also. Now, our goal was, you can recall, to find out what is the stretching in a line element so that we can know the longitudinal strain, for example, at a point, or how much is the shear at a point, how much is the volumetric strain at a point. So we wanted to know the answer to these questions for a general finite deformation. Okay, so let us try to explore that question. So I hope you guys are there. Can someone tell? Are you there?
Yes, sir.
Okay,
Yes, sir.
thank you.
Yes,
It's
sir.
very difficult to understand whether you are there or not. All right, so the next question is, or the topic is stretching of a line element. So again, we have the two bodies, same body in reference and deformed configuration, and I'm at a point capital X, which goes to small x, and then I have a line element. Okay, and we know that delta small x is equal to big F into delta capital X. Okay, and if the line element has got some finite length, then I could also say this is equal to this plus big O delta capital X square, right? Okay, so to know the stretching of a line element, we have to first find out what is the final length of the line element and then divide it with the original length. Okay, so let us suppose I denote stretching by lambda. So lambda. So this signifies stretching. So this is equal to small l by capital L, where small l is the final length and big L is the deformed length. Okay, so what can you say about small l square? So if delta is small x is your line element vector, what will be small l square? Can someone tell me? Yeah, anyone? SP?
सर फाइनल
No.
एंड फॉर्म लेंथ में डिफरेंस समझ में नहीं आया।
क्या समझ में नहीं आया बताना?
सर फाइनल लेंथ और डिफॉर्म लेंथ में डिफरेंस।
सर डिफॉर्म लेंथ की जगह इनिशियल लेंथ होना चाहिए।
सॉरी, नीचे जो डिफॉर्म लिखा है वो अनडिफॉर्म लेंथ है या इनिशियल लेंथ, इसको बोलना है अनडिफॉर्म्ड। अनडिफॉर्म्ड होगा ना, तभी तो मिलेगा स्ट्रेचिंग। तो देखो मैं मिस्टेक भी कर सकता हूँ करने में, तो यू हैव टू पॉइंट इट टू मी। अगर पॉइंट नहीं करोगे तो फिर कैसे समझ में आएगा?
Sir, L square will be the rectangle area of the rectangle. If
कौन सा रेक्टेंगल? विच
we
रेक्टेंगल?
taking a 2D plane element instead of just one line, so each of side L, so square. Sorry, sir, it will not be a rectangle. It should be a square in that case.
नहीं देखो, सबसे पहले हु इज दिस गाय? कौन हो?
Sir, Devjit.
देवजीत, ओके। वेल सी, we want to know the length of a line element.
Yes, sir.
So line element जो है एक line है, right?
Yes, sir.
So this is that line. You see this line here. This is this line. तो इसका लेंथ क्या होगा? It's a vector. इसका लेंथ जो है same as the length of the arrow.
एल डॉट एल और एल ट्रांसफर।
अब एरो का एक पॉइंट स्मॉल एक्स पे है और दूसरा पॉइंट स्मॉल एक्स प्लस डेल्टा स्मॉल एक्स पे है, तो उसका लेंथ, उसका वो वेक्टर क्या हो गया? व्हाट इज द एरो वेक्टर? So this vector is delta small x,
डेल्टा
right?
डेल्टा स्मॉल एक्स। यस
This is that vector. अब किसी वेक्टर का लेंथ निकालना हो तो क्या करते हैं?
मैग्नीट्यूड
डॉट प्रोडक्ट।
राइट, तो मैग्नीट्यूड कैसे निकालते हैं?
डॉट प्रोडक्ट है।
एग्जैक्टली, उस वेक्टर को उसी से डॉट कर देंगे तो मैग्नीट्यूड स्क्वायर मिल जाएगा,
Okay, okay.
राइट?
Yes, sir.
Is anyone here who cannot follow Hindi? Okay, so this L square is then delta small x dot with delta small x, right? So you see, you don't have to look at a rectangle and find the area of the rectangle. I'm just talking about the length of the line element. Similarly, what is this capital L square? That is delta capital X dot with delta capital X. Are you guys with me over here?
यस सर।
Yes, sir.
Okay. Okay, very good. Thank you.
यस सर।
So, all right. Now, what should we do next? Yeah. So maybe I find out lambda square, the stretching square. So that is then delta small x dot delta small x divided by delta capital X dot with delta capital X. Okay, which is same as I write the formula for delta small x, which is f delta capital X plus big O delta capital X square, isn't it? And then I dot it with f delta capital X plus big O delta capital X square. Are you guys with me? And then I divide by, see on the denominator we have delta capital X dot with delta capital X, which is same as magnitude of delta capital X square. Isn't it? See, please interrupt me if you can't follow. No question is trivial, so don't worry if you feel like my question would be silly question. Just don't worry about it. Because sometimes you guys ask question which also makes me to think. Okay? All right, so you see now I'm going to do a very nice thing. On the denominator we have delta capital X square. So why don't I take one of the delta X to one of the bracket in the numerator and the other one to the other bracket in the numerator. So when I do that, I'll get the following: f delta capital X divided by magnitude of delta capital X. You see, how could I do it? Because I'm dividing by a scalar quantity, so I could very well bring it anywhere in the expression of f into delta capital X. And in this case, I have brought it below delta capital X itself. Plus big O delta capital X square divided by delta capital X. Okay? And then I dot it with f into delta capital X divided by magnitude of delta capital X plus the same thing. All right. So now you tell me, what is this? Now this number here, or this quantity over here, what is this signifying?
Sir, unit vector.
Unit vector, exactly. It's a unit vector along the line element, or it's the direction of the line element, isn't it? So let us say this is M, okay, a vector M. Now, what can you say about this term here? So on the numerator, you have a function which is of the order of delta x square. And then you're dividing by delta x. Then what becomes to this order? If a function was x square, you divide by x, then it becomes x. So you see its order also changes. Originally it's ox square, after division it becomes ox. So same thing is going to happen here. This expression then becomes big O delta capital X. Are you guys with me?
Yes, sir.
Okay, so this then becomes f m plus big O delta capital X. You know, the nice thing about this big O is that you don't have to worry whether this term is scalar, vector, tensor, or whatever. You just write it as big O. Okay? And I then dot it with the same thing, f m plus big O delta capital X. All right, so what do I get then? So you see the most significant term here obviously is this one. So this becomes Fm dot with Fm plus what will you have? What do I get if I multiply these two? So Fm is like a constant and I'm multiplying with an order of delta x. So when they get multiplied, it becomes order of delta x only. Similarly, this one is also of the order of delta x. And these ones, they are of the order of delta x squared. So finally, everything can be written as O delta capital X. Is that fine? So what is this? This is the formula for stretching square for a line element which is in the direction of M and located at point capital X. So this is that formula. So for a general deformation, if I want to understand the stretching of a line element in the direction of M, then here is the formula. And as you let the length of the line element go to 0, because only then you will get stretching at a point capital X. If you don't let the length of the line element go to 0, then you are actually looking at stretching in the neighborhood of this capital X. Isn't it? But I want to know stretching right at the point X. So for that, you have to let the length of the line element go to 0, so that it really becomes stretching of the point. Well, it's technically incorrect to say stretching of the point, but we can say stretching at a point. Okay, so stretching at a point means stretching of a very, very tiny line element at that point. That's the meaning of stretching at a point. Okay, and what we see is that this stretching is finally also dependent on the direction. So for different direction of line element, the stretching will be different. So here, by the way, on the right hand side, I have to apply limit delta x going to 0, isn't it? So that you get the stretching at a point. And when I do that, I get a nice formula that this is big F into M dot with big F into M. So you see, this is an exact formula. We didn't do any approximation in deriving this formula. Are you guys with me up to this point? Anybody having difficulty in following, please ask me.
Sir, last term dot प्रोडक्ट का ऑर्डर ऑफ डेल्टा एक्स डॉट ऑर्डर ऑफ डेल्टा एक्स ऑर्डर ऑफ डेल्टा एक्स स्क्वायर होगा ना?
हाँ,
सर
एज आई
उसको
सेड, दोनों को मिला के ऑर्डर डेल्टा एक्स कर दिया।
ओके सर,
बिकॉज ऑर्डर डेल्टा एक्स का मतलब है कि उसमें डेल्टा एक्स वाला भी है, डेल्टा एक्स स्क्वायर वाला भी है, डेल्टा एक्स क्यूब वाला भी है, सब कुछ है।
ओके सर।
ओके, सो दिस इज एन एग्जैक्ट फॉर्मूला। रिमेंबर, इस फॉर्मूला को निकालने में कोई भी अप्रोक्सीमेशन नहीं है। Anybody not following? What about Nomendra? Nomendra Tomar, are you following?
I'm able to follow, sir.
Okay, excellent. So
The stretch will be in direction of M cap.
yeah, so M itself is a unit vector. So you don't have to say M cap. It's a unit vector. So this is the stretching of a line element in the direction of M.
Okay.
And as you change the direction of the line element, you get different stretching. So basically, when somebody asks you what is the stretching at a point in the body, then you have to ask him back, please also tell me what direction you want to look at the stretching. Because at a point there are so many stretching values, right? Because you have, as you change the direction, you get different stretching. And this is also quite intuitive from a very simple experiment. You take a bar and you stretch it along the axis, then you know that transverse direction it compresses. So in the axial direction there is a positive strain, longitudinal strain, but in the transverse direction there is a negative strain. So you can see in this simple example that the strain is dependent on the direction. Okay. Anyway, so what I'm going to do now is I bring this F on the other side. But you know that when I do it, it becomes a transpose. So this becomes F transpose F into M and then dot with M. Okay? And this F transpose F, it's written by C, and this has got a name. This is called Wright-Cauchy-Green tensor. I think you must have learned this in continuum mechanics till now. Did you face this?
Yes, sir.
Yes, sir.
Okay. And had you found out the formula for this stretch? So did you find out
Yeah,
the formula for stretch?
yes, sir.
Okay. So you must have gone through similar derivation, I guess.
Yes, sir. Similar one. The other one was not this much detailed. Like it was from directly from the diagram.
Please say again, it was what?
It was not this much detailed, sir. Like using
Okay.
the order, higher order of delta x and all was not taken much.
Sir, he
Okay.
was just neglecting higher order terms and proceed further.
Okay, so he was not showing at all the higher term. Okay.
No, sir. Yes, sir. Yes, sir.
Okay, I mean, see, although finally it didn't matter, but it is important to understand what we are doing. Okay. So, all right, now we can also express this C in terms of displacement. So first of all, this F, we know that this is also equal to, I mean, this is gradient of small f, which is same as gradient of capital X plus u, right? Because small f is capital X plus u. So this is same as gradient of capital X plus gradient of u. Okay. And by the way, you have to remember that these gradients are Lagrangian gradients with respect to undeformed coordinates, not with respect to deformed coordinate. So basically they are del by del capital X. It's not del by del small x. So it's called Lagrangian gradients. So the first term, gradient of x, what will this give me? So it's a second order tensor and its component will be del of capital Xi over del of capital Xj, which is delta Ij. And so it becomes an identity, isn't it? And the next one is simply grad u. So what is then F transpose F? So F transpose F is then identity plus grad u transpose into identity plus grad u, okay, which is identity plus grad u plus grad u transpose plus grad u transpose into grad u. All right, so this is the right Cauchy green tensor expressed in terms of displacement gradient. If I want to know what is Cij, the component Cij, then what do you think? What will this be equal to? So Cij, if I do it through F transpose F, then can I say that this is same as Fki into Fkj? Because you see C is F transpose F, so it's a simple multiplication. So basically C is equal to the matrix F transpose multiplied with the matrix F itself. So Cij is Fki into Fkj, the components. And from here Cij is delta ij plus del ui over del xj plus del uj over del xi plus, here is the quadratic term. This is quite interesting. This is del uk over del capital Xi into del uk over del capital Xj. Because you see the first one is transpose, therefore it becomes del uk by del xi instead of del ui over del xk. Are you guys following?
Yes, sir.
Okay, very
Yes,
good.
sir.
So anyway, so this was your C, right Cauchy green tensor, and you will see that this is going to appear so many times. So by the way, we just got the stretching square. So what will be strain, longitudinal strain? If I want to know longitudinal strain in the direction of M.
Sir,
Yes,
sir, what does capital C physically signifies? For example, this capital F was transforming the delta of capital X into d of capital into small x.
yes, yes. So that's a very good question. It will become more clear as we talk about various kinds of strains, longitudinal strain, shear strain, volumetric strain. So you will see that it is appearing in all kinds of strains. So it is related to strain. So it signifies, strain in the body. Okay. So anyway, so longitudinal strain, if I denote it by epsilon, then again it is a function of the point in the body where we are measuring it and also the direction of the line element M, and it is simply equal to lambda minus 1, and lambda we just saw that it is equal to C M dot with M, isn't it? And it has to have a square root also. Okay, so so what will be this? Yeah, so I have to subtract a 1 also to get longitudinal strain. Okay, now let us try to work this out. Now, if I express this in terms of gradients, okay, displacement gradients, then this is identity plus grad u plus grad u transpose plus the other term, grad u transpose into grad u, right? And okay, so this thing then gets multiplied with m and further dot with m minus 1. So this implies your epsilon at a point capital X comma m. Please point to me if you see that I am making a mistake. It's very much possible. So the first term is identity into m. What is that? That's m itself, and dot with m, it becomes 1. Okay? So this is also equal to 1 plus the remaining term, okay, the remaining term. And you see this remaining term, can I say and write it as c minus I, okay, of m dot with m. Isn't that? I can very well do it, and then I have to subtract with 1. Now let us understand what is the order of this term over here. So if you look at c minus I, this is this c minus I, no? These two are the same thing. So, and you can see that it has got terms which is linear in displacement gradient and the term which is quadratic in displacement gradient. Okay? And you know, in your first year, sorry, in your undergraduate strength of materials course, it was always assumed that displacement gradient is very, very small. Basically, the displacement is happening such that each of the derivatives of displacement with respect to x, they are small. That means I can also write it here. So in undergraduate or in UG strength of materials course, del ui over del xj. So for each of I and j, they were assumed to be much, much less than 1. No, for example, of the order of 0.1. Okay? So if that is the case, this green term over here, this green term over here, for such a scenario will be a very small number. Okay, it's going to be a very, very small number. And in that case, so if this is the case, then your epsilon of x comma m can be written as, approximated as 1 plus half of c minus I, okay, m dot m minus 1, which is equal to half of c minus I m dot m. And furthermore, because the displacement gradient is very, very small, so the quadratic combinations will be even smaller. So basically, from this term over here, I can neglect this quadratic term. Quadratic term can be neglected. If del ui over del xj are much, much less than 1. because you see it has got a product, no? So it becomes even smaller. That's what we learned in the strength of materials, first in the UG strength of materials. And in that case, it was further approximated to be half of grad U plus grad U transpose into M dot M. So this is your UG first year, epsilon x comma M. Sorry, UG second year, I guess. You learned it in second year. So UG SOM, this is what you did, and which holds only for small displacement gradients. But now in your PG courses, this is the formula for epsilon. And this holds for even large deformation. Okay? And this term over here, you see, you saw it at C minus I, no? This C minus I. So we also define the what is called Green Lagrange strain tensor. Green Lagrange strain tensor. And it is denoted by epsilon. And it is equal to half of C minus I, which is same as half of grad U plus grad U transpose plus grad U transpose into grad U. So it has got also quadratic term in displacement. Okay, so basically, and you can also say that epsilon ij is then equal to half of del ui over del xj plus del uj over del xi plus del uk over del xi into del uk over del xj. And this tells us that strain is non-linear in displacement. So for large deformation, this strain definition is non-linear in displacement because of this quadratic term here. Okay, this makes it non-linear. And this quadratic term is neglected in your second year UG solid mechanics course. Okay, any question till now? Please interrupt me if you feel like I'm missing something, or if you know something which I have not discussed. Feel free to talk to me. Feel free to say.
Sir, hello, sir.
Yes.
Sir, in the previous one, sir, you are deriving the deformation gradient tensor by assuming, by neglecting higher order terms, just assuming that it is a case of infinitesimal line element.
Yeah.
And here you are assuming that that you have studied in your UG course that for small deformation we are neglecting the quadratic term. Sir, is there a relationship between the infinitesimal line element and small deformations?
No, there is no relation. There is no relation. See, why did we talk of infinitesimal line element? That's because I want to understand deformation at a point. At a point. Or I want to find out stretching at a point. shear strain at a point, which means I have to look at line elements which are very, very small. So that's why we said that delta capital X is going to 0. And this has got nothing to do with linear or non-linear elasticity. Whether you are talking of linear elasticity or non-linear elasticity, your line elements have to be small, because I want to know what is happening at a point. If I take line elements to be of finite size, then I won't be talking about deformation at a point, right? Because it's a finite size, so it also contains points in the neighborhood of the point itself.
Uh, yeah. Sir, that means whatever I have studied during my UG course derived just by assuming in infinitesimal line element. That means here we are studying.
Yeah, of course, that was derived, that was for infinitesimal line element and also for small displacement gradient.
Uh,
Your UG course, you not only talked of small line elements, but also for a small displacement gradient. The displacement was such that the displacement gradients were small. Only then you could neglect the quadratic term in the definition of strain. You see, now when you worked out everything in the most general way, the strain came out to be um, also containing this quadratic term, isn't it? It also
yes,
has
sir.
this quadratic term. So this is the most general formula having no approximation.
Okay, sir.
But in your UG course, you have neglected it because you had assumed that displacement gradient is small.
Okay,
And
sir.
that, and it has got, it's not like, this is of no use, this assumption. This assumption is of very vast use. Most of the machines that work, if you go to a workshop and look at a machine vibrating, the vibrations are very, very small. And then it is very safe to assume that displacement gradients are very, very small. And then you can use linear elasticity. But suppose, a machine is vibrating, you look at a lathe machine or a cutter machine, and it goes into a resonance regime. Or let us suppose an aircraft is flying and it has got an engine, so it's rotating such that it goes into resonance, so the amplitudes are going to become very, very large, and in that case this displacement gradient being small does not work, and then you have to look for finite deformation. Even for soft matters, they deform a lot. You take a rubber, you can deform a lot. So there, it's not a good assumption to say that the dispersion gradient is small.
Okay, sir.